Hello, everyone. So here today, I gave a talk at Sarah Lawrence called Visualizing Set Theory, and it went great to undergrads. A lot of some of my students were there. And so there was no recording, so I just want to share with you guys, anyone that wants to watch the slides and just some of what I talked about. Okay, so I think maybe some people from the internet might show up, so we'll see. See, it's kind of hard to tell what's going on. Okay, so let me just Okay, so I'm recording this now. I'm trying to get the full screen. Let's see if that works. Okay, do that. Okay, I'll get this to work just a second here. Okay, here we go. So okay, so I'm gonna get started here, and if anyone has any questions, I know maybe there's a person here. Feel free to just ask. Okay, so here's the talk was on November 15th and Tuesday. Okay. So okay, so thank you for letting me come here today to preach to you about set theory. Set theory is cool. That's the main point of the talk. If you like real analysis, combinatorics, linear algebra, number theory, I think they all have set theory has like kind of some of the flavor of all of those. So if you like those, you might like set theory. Also, I think that if you like art or philosophy, you might like set theory. And set theory revolutionized mathematics both horizontally in uncovering the axioms, its foundations, and vertically by letting us touch the stars, the higher infinities. So some of the things I want to talk about today are ordinals, cardinals, the cumulative hierarchy, and the axioms. And these are 4 important topics in set theory. And on top of that, I'd like to talk about large cardinals, and which themselves are entire universes. So we can't prove they exist without violating Gödel's incompleteness theorem. And so they are cardinals. But about 85% of this talk is going to be about ordinals and cardinals, and I'll just mention some of these other things at the end. Okay, so first up, ordinals. So ordinals are special sets. They have a fractal nature, and they help us count the length of a set. The finite ordinals are the natural numbers. And so in order to see the fractal nature of the ordinals, so I'm going to replace the set brackets with a circle, a circular-ish shape. And so I realized I haven't really said what a set is, which is what set theory is about. But intuitively, it's a collection of objects. So this is the set that contains T. And so eventually I want to get to what's this fractal nature of the ordinals. And I think if we use like a circle and circles instead of these set brackets. With the set brackets, you can't really see, it's kind of hard to see what's actually going on in these sets. So that's the idea, is we have a circle. And in set theory, we can make any set with just the set brackets and the empty set. I mean, the empty set can be expressed in brackets too. It's the brackets with nothing inside of them. And the empty set is the set that has no members. So since I've been more aesthetically pleasing symbols. So I've been wondering whether to use like a dot or a circle, because I guess technically the empty set would be just a circle with nothing in it. But when you're making these pictures, it's kind of easier to see when you have an actual symbol for the empty set. And I think also, like, when you're writing with set brackets, you're writing the ordinals with set brackets, it's nice to have a symbol for the empty set. It's just like one less layer. So I decided to go with this sort of compromise of a dot. It's like a little circle. Sometimes it gets so small that it's like just looks like a dot, but this is the empty set. So this set is the set that contains the empty set and the set that contains the empty set. Okay, and I said, well, I must confess that for a long time I actually got confused between nothing at all, absolutely nothing, and then the empty set. So the empty set is a set. It is a set. It has these set brackets. It just doesn't have any members at all. Okay. But yeah, I was mistaken for a while. Okay. So besides the equality relation, the language of set theory consists of the binary relation, this epsilon, the membership relation, or you can think of it as the element of relation. And A is an element of B if A is one of B's members. So we can see here that B has A as one of its members. We can see that B has three members, and A is one of them. And something very closely related to the membership relation is the subset relation, and that is defined in terms of the membership relation. And they kind of look similar. So a subset, A is a subset of B if every element of A is also an element of B. Okay, so we can see that A has two elements, the empty set and the set that contains the empty set. And so we can see that, oh, B has those two elements. So to see if something's a subset, just look at each element of A and say, okay, A has, if A has the empty set, B should have the empty set. If we're saying that A is a subset of B. And if A has the set that contains the empty set, then so should B. And so we do have that here. But notice that A is not actually an element of B here. It's just a subset. And I guess the empty set is always a subset of every set because it doesn't have any members. So there's nothing to check. Okay, so one of the things that an ordinal is, it's transitive. And it's like half of its definition is that it's transitive. A set is transitive if every member of every element of T is also an element of T. And so you can see there's this set looks kind of fractal-like, kind of. It seems like it's this. There's something tying these all together. There's some kind of, I don't know if you want to say unity or something, but okay. But let's see if this. So this is a transitive set, and so this set has 5 elements, and this is I don't know why I picked this set like this, but this set has 5 elements, and each element has only 1 element. So what we should do to see if T is transitive is we should go to each of its elements, look at its elements, and see if that's an element of T itself. Okay. So look at this element of T. It has 1 element, this like the set that contains the set that contains the set that contains the empty set. Okay. Let's just look at the picture. So this has 1 element. And so if this shows up this should show up in T somewhere because I'm claiming this is transitive. And then there it is right there. Okay. Now let's go to this element of T. It has 1 element. So that should show up as an actual member of T. And there it is right there. Okay. And then we have this, this element of T. We look at, it only has 1 element. So that should also be an element of T if it's transitive, which it is right there. And we don't have to check the empty set, right? Because there's no elements, so it's automatically a subset. Okay, here's another transitive set. Let's check and make sure that it is. Okay, it looks kind of, I'm trying to just see like, well, when you see the ordinals, you'll see like they're very like, oh, that's something special. These look, there's something nice here though. It's like, there's something like there's some communication between the elements or something like that. But let's just see if it's transitive. So yeah, transitive sets are nice. So this set T has 1, 2, 3, 4. Wait, 1, 2, 3, 4, 5, 6 elements. Okay, so let's just check each of its elements and see if it's a subset. Okay, so this element has 3 elements, so those should actually show up as elements of T. Okay, I think we can see them there. Okay. And let's go to this element of T. It has 2 elements. Those should show up. They do. This has 1 element, and it's right there too. And this has 1 element. That's right there. Okay. And then the empty set, we don't have to check. Okay, so this is transitive. Here's some examples of sets that are not transitive. Okay, you can see, like, I mean, just looking at it, it's like, it doesn't look as nice or something as the other ones. Well, they're not even trying here. So it's like, this has 2 elements. None of them are elements of T. This has 1 element. It's not element T. This has 1 element. It's not element T. Anything that has just 1 element, unless it's just the empty set itself or the set that contains the empty set, if it just has 1 element, it's going to be hard to be transitive. So this is not transitive. This set also just has, 1 element, and that's this element here. Okay. Okay, and again, if anyone has any questions or anything, let me know. The other part of being ordinal is that a set is an ordinal if it's it's well ordered according to epsilon. But here's the definition of well ordering. So an order P is a well ordering if every non-empty subset of P. What does it say? A linear order? Oh, linear order. Sorry, a linear order P is a well ordering if every non-empty subset of P has a least element. So if an example of something that's a linear order that's not a well ordering is the integers, because the integers themselves don't have a least element. Okay. Or maybe just the reals between 0, 1. I think that's also not well ordering. But the ordinals are. Okay. Let's see what. So this is finally the definition of an ordinal. A set is an ordinal if it's transitive and well ordered by epsilon. So that means that all of the elements of an ordinal can, I'll say, communicate with each other. They're either one is an element, A is an element of B, or B is an element of A. These are 2 elements of an ordinal. So let's just see. Is this an ordinal? It looks kind of like it's kind of nice. It's like, maybe this is 5 because it's like 1, 2, 3, 4, 5 or something. But let's just see if it is an ordinal. We know it's transitive. So is it well ordered by epsilon? Okay, so some of these fit inside of each other. Like you can put this is an element of this one. This is an element of this one. And they all kind of stack up. This is an element of this one. But this is not an element of this. This only has 1 element. The set that contains the empty set. And this is not that. Also, like, how are you going to compare these 2? You can compare. How can I compare these 2 also, as far as epsilon goes, or membership? I can't compare those 2. Okay. I mean, this looks smaller or something, but we're just saying, like, can you order them with epsilon? Okay, you should be able to compare everything. Okay, so this is the other transitive set that we had. It also looks kind of nice. It could be an ordinal. Let's see if this one's a little better. Let's see, like, so this can fit in here, and this can fit in. Oh, see already, this set doesn't have the empty set as an element, so I can't compare these 2. This isn't an element of this, and this isn't an element of this. These 2, how am I going to compare? Oh, actually, no, that can't. These 2, how am I going to compare? This isn't an element of this one, and this isn't an element of this one. Or these 2, how can you compare them? Okay, so this is not an ordinal, but it looks nice. It's close. We'll see some ordinals. The class of all ordinals is denoted by ord. And so we define the ordering alpha is less than beta if and only if alpha is an element of beta. So some facts about ordinals. This less than, which is defined by the membership relation, is a linear ordering of the class ord. For each alpha and ord, alpha is the set of all beta less, it's the set of all ordinals less than it, set of all beta less than alpha, which is kind of what like the idea is in the first place. And here's a nice one. For each alpha and ord, alpha union, the set that contains alpha is an ordinal. And so that's how we can get to the next ordinal. So you can see this is, if this is alpha, whatever's going on, it's got some members. And alpha union, the set that contains alpha, would be this set. It's got all of alpha's members, and then it's got alpha itself. And so you can see it looks kind of like self-similar, like a fractal. So that's how we define the successor of alpha, of an ordinal alpha. Alpha plus 1 is alpha union, the set that contains alpha. So we can, and maybe we should go to this definition. Oh, maybe not. Maybe we should just go back here real quick. Just think about like some extreme examples, like the empty set. Empty set doesn't have any members, so it's transitive. Well ordered by epsilon doesn't have any members. Okay, so the empty set is transitive and well ordered by epsilon. So the empty set's an ordinal. And then like using this idea, we could say then the empty set union, the set that contains the empty set, is an ordinal. So that's really just the set that contains the empty set. Okay, so we can start building some ordinals with this operation. Okay, so this is the successor of alpha. And if alpha equals beta plus 1 for some beta, alpha is a successor ordinal. If alpha is not a successor ordinal, then it's the supremum, or the least upper bound of all the betas below it. So union of alpha, or union of all beta such that beta is less than alpha. So it's a limit ordinal. So like the natural numbers, those are all successor ordinals, 1, 2, 3, 4, 5. And then the first limit ordinal is omega. And it's the union of all of the natural numbers. Okay, but we'll see some more omega. So we denote the least non-zero limit ordinal as omega, or just with the natural numbers, the boldface type there. The ordinals less than omega are called finite ordinals, or natural numbers. And so 0 is the empty set, 1 is 0 plus 1, or the set that contains the empty set. 2 is 1 plus 1, so the empty set and the set that contains the empty set, and so on. And 3 is 2 plus 1. So let's see what some of these ordinals look like. So the empty set is just the dot, or the little mini circle. 1 is the set that contains the empty set. 2 is the set that contains 0 and 1. And we can see already it starts looking like fractal. Okay, so here's 3. It has 0, 1, and 2 as its members. And you can see it's transitive and it's well ordered by epsilon. This is an element of this. This is an element of this. I can compare them all. Here's 4. So 1, 2, 3, 4. Transitive, well ordered by epsilon. Here's 5. And you can see it looks self-similar. Okay, so for now I want to show some art from different artists, mostly from students of mine, but I tried to find more actually, but I had one, I couldn't find it at the end. But this artist is that's really great art. Jennifer Padilla, I believe that's how it's pronounced. Okay. So she shares her love of science and math through art. And Jennifer has a PhD in biochemistry and an MA in math, and has exhibits all over the world. These pieces here, these ordinal pieces, are made digitally and printed on metal. Okay, so here's her empty set. And this is 1, the set that contains the empty set. Okay, this looks like 2, the set that contains the empty set, and the set that contains the empty set. And here's 3, 0, 1, 2. Here's, let's see if we can, 1, 2, 3, 4, 5, 6. I believe that's 6. Okay, this, I don't know what this one is. Maybe like 100 or something. I don't know. Maybe it's 10. I don't know. But it's, I don't know. I should look it up. So here's some of her work, the von Neumann ordinal series. And yeah, it'd be neat to see these up close. Okay, so she did more of like a square shape, and then they're all like put into this nice, like the overall square shape, really nice. Okay, and then this summer, so the other art I want to share is from students. This summer I taught infinity and art class, but it was mostly like artists and writers, and but one of the assignments, just a homework assignment, was to make the ordinals up to 5. And I just showed them a little bit on a whiteboard thing. And so had some nice results from that project that I wanted to share. Okay, this is Georgia. So this is the assignment, and she has a nice like artistic style. It looks like a chalkboard. And also you can see like some kind of ordering for these ordinals. Okay. Here's Ariana. She did this digitally. And yeah, I like how she used the colors so you can see the sets. You can see like this, this number 4 is an element of 5. So it's nice. And she used the dot for the empty set. Okay, I love that's a great job. This was Nico did more of like a square. I hadn't shown them any of the other art at this time, but it reminds me of that Jennifer's way of doing it. It's a little different, but so she did empty set. One is, I did tell them use some symbol for the empty set, and then something for set brackets. One is a set that contains the empty set. So 2 is a set that contains, choose different colors too. The set that contains the empty set and the empty set, and then it says 3, 4, 1, 0, 1, 2, 3. Okay, nice colors and everything, and trying to put it into like a rectangle, and a really unique way to do it. Okay, here's Luca. I have a few from Luca. He had a couple different ideas. So this is with the dots and circles, and then he started something else up here. But here's his 0, 1, 2, and then sort of making this efficient use of the grid. We can't quite get it into like a square or rectangle easily, maybe, but these are nice. They seem natural, this shape that he's using, because you can keep building bigger and bigger. So here's 4, looks like a spaceship or something. That's really cool. Here's 5. I mean, you can see there's a kind of a natural shape because you could build off this and it could look similar. Oh, that's nice. Okay, here's another one, last one from a student or from anyone. This is 5, and then this is nice because it's showing the order, because they're ordinals and there is an order to them. So it looks great. It looks like a machine, or I don't know, some kind of ordinal gears or something. Very cool. Okay, so and then we can maybe use this idea to visualize the higher or the infinite ordinals. So this is omega. Omega would just keep have bigger and bigger sets that are the natural numbers, and omega itself is the whole set of natural numbers. Okay, so sometimes it seems like, or maybe I've previously thought it's like the thing at the end of the rainbow, or the thing at the top of the stairs, but it's the whole rainbow. It's the whole set of stairs. And so but you might want to think about omega. So omega is infinite, but notice that it doesn't have any infinite members. All of its members are all finite. All of its members are natural numbers. And this is just to like start getting like, what's the difference between these different infinities? So for example, so here's omega plus 1. Omega plus 1 is all the ordinals. I'm sorry, all the finite ordinals, and then omega itself. So omega plus 1 it's omega union, the set that contains omega. So it has all these finite ordinals, and I tried to make them kind of, did I mess up? I think maybe I'm missing, it looks like maybe I'm missing something right there. I think I'm missing this 2 here. But so omega plus 1 has, it's infinite. It's also infinite, just like omega, but it has also an infinite member, and also it has a greatest element, so it's different from omega. And later we'll talk about cardinality, and if you already know about one-to-one correspondences, notice that there is a one-to-one correspondence between omega and omega plus 1. If I just say this is 1, 2, 3, 4, 5, 6, and so on, and I could do the same thing, 1, 2, 3, 4, 5, 6, and so on. We can match them up. So they're the same size, same cardinality, but they're different, like, order types, and then different elements and different properties. Okay, I kept going. It's kind of natural to make ordinals on digitally because you're like copying and pasting a lot. Okay, so I want to try one more level. I think did I get that one? Oh, I'm making all these mistakes. Okay, this should have the empty set in it. I don't know what's going on. Okay. Anyway, this is omega plus 2, and it has all the finite ordinals, and then plus omega and omega plus 1. So this is something that's infinite. It has infinite members. It has 2 infinite members. It's also the same cardinality as omega, because we could just say this is the first one, second one, third one, fourth one, fifth one. So with ordinal arithmetic, we have addition defined. And so notice these 2 rules. Okay, alpha plus 0 is alpha plus beta plus 1. So like if it's a successor ordinal, then it would be alpha plus beta and then plus 1. So for example, if we did omega plus 1, okay, that's just omega plus 1. Maybe I should think of like omega plus omega plus 1 would be like omega times 2 plus 1. But I think omega plus 1, so I want you just to keep in mind omega plus 1. So omega plus 1 is a successor ordinal. So omega plus 1 is just omega plus 1. We've already seen it, but it's a new ordinal, different than omega. Okay, and if the second term here is as a limit, then you take the limit as xc goes to beta alpha plus xc for all limit. So for example, 1 plus omega, if we use 1 plus omega, we use this rule. So that'd be the limit as n goes to omega of 1 plus n, which is still omega. Okay, so there's a difference if you're adding a limit ordinal second or first. And so for multiplication, and I'll show that example in more detail in a second. For multiplication, alpha times 0 is alpha times beta plus 1. It's like you can distribute the alpha, but again, it's 2 different rules. So if we did alpha times 2, I'm sorry, if we did like omega times 2, 2 is a successor ordinal. So that would be like omega times 1 plus omega, or omega plus omega, or omega times 2. So that's different ordinal. If I do 2 times omega, I'd use this rule. And so that would just be the limit as n goes to omega of 2 times n. But that's just omega, okay? So that's like taking like a regular limit, 2 times x as x goes to infinity is like infinity, right? So let's see that. Okay, so exponentiation, alpha to the 0 is 1. I'm not really going into much detail of any of this stuff, but you can see there's some properties that maybe remind you of the way that the real numbers work, or naturals for the exponentiation. But there's like there's differences. Okay, and then again, the different rules for exponentiation based on if it's a limit ordinal or a successor ordinal. So here's showing that addition is not commutative. So 1 plus omega, because omega is in the second spot and its limit ordinal, is the limit as n goes to omega of 1 plus n, which is omega, which is not the same thing as omega plus 1, which we saw. Okay, 2 times omega is not the same as omega times 2. 2 times omega. The omega is in the second spot, and it's a little bit ordinal. So this is the limit as n goes to omega of 2 times n, which is just omega. And just think of like you're taking a regular limit. Limit as n goes to infinity. Okay, this is not equal to omega times 2. Omega times 2, now the 2 is in the second spot, and that's a successor ordinal, so it's omega times 1 plus omega, which is omega plus omega. So these are different. This is if you're maybe an undergrad taking a proofs class and you've seen induction. So if you like induction, you're gonna love transfinite induction. We have a base case or an anchor case. Let C be the class of ordinals and assume that 0 is in C, and that if alpha is in C, then alpha plus 1 is in C. That's like the regular induction hypothesis step. Deduction hypothesis, induction conclusion. I don't know. If alpha is non-zero limit ordinal and beta is in C for all beta less than alpha, then that implies alpha is in C. If that happens, then C is the class of all ordinals. So it's just like regular induction or common induction, except that you have a limit stage. It's kind of like strong induction. Okay, so I just want to show this just so if people are undergrads and they want to take maybe set theory at some point, it's like they got a similar feel to a proofs class or maybe an intro to real analysis. So here's something that we can prove with transfinite induction. We can prove these associative properties of multiplication and addition, for example. Also another thing we can prove with transfinite induction is Cantor's normal form theorem. So I just want to mention it. It's a really cool theorem. Every ordinal alpha greater than 0 can be represented uniquely in this form. Omega to the beta sub 1 times k sub 1 up to omega to the beta sub n times k sub n, where these k's are the betas are in decreasing order, and the k's are non-zero natural numbers, which is kind of cool. Like it's almost like, I don't know if this is totally the right way to think of it, but it's like every alpha has this list of natural numbers that's sort of like its code. I mean, you also have these exponents here, but it's a finite expression. And okay, it reminds me of prime factorization theorem, something like that. And we can see in the proof, this is all from Yek, by the way, all this, the whole presentation is from the theorems and definitions are all from Yek. So this, we can just go briefly over this. Proof by induction on alpha. For alpha equals 1, we have 1 can be written as w to the 0 times 1, and that's in that form. For arbitrary alpha, let beta be the greatest ordinal such that omega to the beta is less than alpha. And then we have this lemma that's like the Euclidean division algorithm, which is really, that's like how you prove the prime factorization theorem. We need this Euclidean division algorithm. There exists a unique delta and a unique rho, with rho less than omega to the beta. That's like your remainder in the Euclidean division algorithm, such that alpha equals omega to the beta times delta plus rho. This delta must be finite, otherwise we can get another power of beta of omega less than or equal to alpha. So, and the uniqueness of the normal form is proved by induction. Okay, just to see. Okay, cardinals. So there's like cardinal numbers, and then there's the concept of cardinality. So two sets have the same cardinality if there exists a one-to-one mapping of X onto Y. Okay, so I thought if you haven't seen one-to-one onto mappings, I just show this. Okay, so we have these mice and these, cats and these mice, and it's a map from cats to mice. This is a one-to-one, meaning each mouse that gets hit, it gets hit by only one cat. So each cat, it's a function, so each cat can only point to one mouse. But when it's one-to-one, no two cats point to the same mouse. Okay, so one-to-one. These guys didn't even get hit. Okay, an onto map is one where everything in the range gets hit. So in this other one, we had some mice that were involved in this function. And when you have onto map, then everything in the range gets hit. So, or should I say everything in the codomain gets hit? Okay, maybe I should say everything in the codomain gets hit. Okay, so okay, so we have all the mice got hit. So this is an onto map, and a one-to-one and onto map is one where it's for each mouse, every mouse gets hit, and there's only one arrow. It only gets hit by one cat. Okay, and so what it does is and I could have drawn these arrows like crossing or something. It's just limitations of PowerPoint, kind of. But these two, you can see that there's, when you have one-to-one onto correspondence, you can count, then they have the same, sets have the same size. So this is 6 cats, 6 mice, and that's how you can match up things that have the same cardinality with a one-to-one and onto map. Also called a one-to-one correspondence. The cardinality relation is an equivalence relation, thankfully. So since the cardinality of n and the cardinality of m are the same, if and only if the two natural numbers are the same, we define the finite cardinals as natural numbers. So the cardinality of natural number n, finite number n, is n. So we're defining like cardinal numbers from cardinality. So two sets have the same cardinality. I guess you could just not even mention what that cardinality is. We're defining cardinal numbers. So the finite cardinals are the natural numbers. Okay, so in general, okay, an ordinal alpha is a cardinal number. So all of these cardinal numbers are ordinals. So we're still working with the ordinals, and just some of them are special. All the ordinals are special, but some of them are more special. An ordinal alpha is a cardinal number, or a cardinal, if the cardinality of alpha is not equal to the cardinality of beta for any beta less than alpha. So then anything below it, any ordinal below it has a smaller cardinality. Or you can say it's the least it's the least ordinal with its cardinality. You could say it that way too. So it's like so it's like let's see a picture. Maybe I feel like, okay. Every finite natural number is a cardinal, but I think you guys can, I think everyone can see what's going on with it's like the first of its kind. The first ordinal with that cardinality is a cardinal number. Okay. Every natural number is a cardinal. If S is a finite set, then the cardinality of S is n for some n. The ordinal omega is the least infinite cardinal. And all infinite cardinals are limit ordinals. For every alpha, let alpha plus be the least cardinal number greater than alpha, the cardinal successor of alpha. The infinite ordinal numbers that are cardinals are called alephs. So we can define the increasing enumeration of all the alephs. So the aleph naught is omega sub naught, or just omega. Aleph sub alpha plus 1 is is omega sub alpha plus 1, and it's the next cardinal alpha after aleph sub alpha. If alpha is a limit ordinal, so all these are indexed by ordinals. If alpha is a limit ordinal, then it's the supremum of the omega sub betas, such that beta is less than alpha. We usually use aleph sub alpha when referring to a cardinal number, and omega sub alpha to denote the order type. So here's a chart. So this is showing that omega actually is, aleph naught actually is omega. But all of these ordinals have cardinality aleph naught. And then we get a new cardinal number when we jump to a new cardinality. So aleph sub 1 is uncountable cardinality. It's the next cardinality after aleph sub naught. And so all of these have the same cardinality as omega sub 1. And there's a lot here, like omega plus 1, omega times 2, omega squared, omega to the omega, omega to the omega to the omega to the omega. These are all still countable. epsilon 0 is omega to omega, omega many times, still countable. You can add 1 to that, keep going. So there's a lot going on here. But at some point, there's a next cardinal, and that the first ordinal with that cardinality is actually alpha 1. Okay, we'll keep going. And so anything that's cardinality, these are infinite, I'm talking about infinite sets. Anything with cardinality aleph naught is countable, and anything with cardinality other than aleph naught is uncountable. The index will tell you whether it's a limit or a successor cardinal. 0 counts as a limit, so aleph 0 is a limit, aleph 1 is successor, aleph 2 is successor. The next limit after those is aleph sub omega. Okay, for cardinal arithmetic, we won't do much with these, but right now, kappa plus lambda is a cardinality of alpha union beta, where cardinality of alpha is kappa, cardinality of beta is lambda, and alpha intersect beta is empty set. I will talk about, like, here, I'll just let you guys read that. This right here. So if I 2 to the lambda would be beta many sets of, like, the set 0, 1. So, like, think of like a product of 0, 1 of the number 2 being 0, 1, set 0, 1. Okay. So that cardinality would be like all the binary sequences of length alpha, or length lambda, if I said 2 to the lambda. Okay. The cofinality of an ordinal, denoted, sometimes people write COF, actually that's probably more common, COF alpha, is a least limit ordinal beta such that there's an increasing beta sequence with the limit as xe goes to beta alpha. Okay, so this is a transfinite sequence. We can have different in proofs class or in real analysis, we have a sequence really of length omega, but we can have now sequences of length omega plus 1, I guess, or we can have sequences of length omega sub 1. This is, so not every, so the cofinality of ordinals is not necessarily itself. It might be shorter than itself. So here's omega plus omega. So omega plus omega is like 0, 1, 2, 3, 4, the whole thing of omega, and then in omega plus 1, omega plus 2, up to omega plus omega. Aleph sub omega is the union of all of the aleph sub n's. So if we can think of it as omega sub 1 followed by omega sub 2, and we just keep going up these ordinals until we get to aleph sub omega. Aleph sub omega would be the union of these. Okay, and but we can find a sequence shorter than them whose limit is them. So I can get to omega plus omega with this sequence, omega plus 1, omega plus 2, omega plus 3, and that's only a sequence of length omega. So that's why the cofinality of omega plus omega is omega. And this one here, the sequence here, omega sub 1, omega sub 2, omega sub 3, they're indexed by naturals. And so this is also a sequence of length omega. So the cofinality of aleph sub omega is also omega. Okay. So an infinite cardinal aleph sub alpha is regular if the cofinality of omega sub alpha is omega sub alpha. And so those other cardinals were not regular, or I guess aleph sub omega is not regular. Okay, there's not really a cardinal for omega plus omega. Okay, just in case anyone hasn't seen what a power set is. So when with cardinal numbers, we've seen that, like, you can multiply omega times omega, take powers. You don't get anywhere as far as a bigger cardinality goes. But when we take power sets, we get a bigger cardinality. Okay, there's just exponentiation alone. But when we take a power set, I think so. Okay. So a power set, so you're going to a picnic, there's these 3 fruit items available, and you can choose anything you want. and you can choose nothing at all. You can choose all three. You can choose two of them or one of them. And so it's a power set is the set of all subsets of a set. So this is all the subsets of this 3-element set. And notice that this has 3 elements and the power set has 8. And so then that's true with all finite numbers, that the cardinality, if a set has cardinality n, then the power set has cardinality 2 to the n. And the same is true for the infinite sets. If A has cardinality kappa, then the power set of A has cardinality 2 to the kappa. So just for the proof, consider the characteristic function for A. And this is a one-to-one correspondence between the power set of A and 2 to the kappa, or these are like, you could think of all the binary sequences of length alpha, of length A, of length kappa. Okay. So one great thing is that we take power set, we get a bigger set. We get a bigger set, and we also know how big it is, 2 to the kappa, if the original set is size kappa. So this is Cantor's theorem. This is great news. This is how we can get to bigger cardinalities. And so this says for every set X, the cardinality of the set is strictly less than the cardinality of its power set. So let's have a function from X to P of X. This set Y, the set of all X and X, such that X is not in its image, can't be in the range of F. If it is in the range of F, there's some Z such that F of Z equals Y, then Z is in Y. You get into Y if and only if Z is not an element of F of Z, but F of Z is Y. So Z is in Y if and only if Z is not in Y, contradiction. So F is not a function of X onto P of the power set of X. So the cardinality of X can't be equal to the power set of X. And it's definitely smaller. I mean, it's definitely less than or equal to it to start, because X is an element of power set of X. Okay, and just briefly, these last two topics, the cumulative hierarchy. So once we have the power set, we can, just with the empty set and the power set, we can make a place where all the sets live. And so start with the empty set, and then take the power set of the empty set to get V1. So these are different levels in the hierarchy. V0 is the first level, V1 is the next level. V2 is the power set of V1. And then for each V alpha plus 1 is the power set of V alpha. There's like a little mistake here. This should have like an extra circle or something. These two sets are the same, but that's the idea. And so notice also that when you're doing this cumulative hierarchy, I think I have another picture here. When you're doing this cumulative hierarchy, okay, so you take at each successor level, you take the power set of the thing that came before. If there's no thing that came right before, you take the union of all the levels that came before. So V sub omega is the union of all the V sub n's. But notice that none of those V sub n's include omega itself. So that won't enter the hierarchy until V sub omega plus 1. But notice these blue sets are all the ordinals. Each level in the hierarchy gets one new ordinal. I guess V sub omega didn't get any new ordinals. But the ordinals sort of, for successor stages, I guess each successor stage gets a new ordinal. Okay, if I'm saying something wrong, let me know. But there's only like one per level basically, and they're these special sets. Okay, they sort of like keep track of what's going on. And then the V is the whole union of all these V alphas, and there's a theorem that says for every X, there's an alpha such that X is an element of V alpha. So every set enters the hierarchy at some level. Okay. So this thing is sort of like this cumulative hierarchy of sets is like, I don't know, like a place where you could do all of mathematics. Maybe you could, this cumulative hierarchy is something that turns out also models the axioms of set theory, or the axioms of mathematics. So I just took the axioms from Yek, just copied, just screenshotted the axioms from Yek, and a lot of that cumulative hierarchy that I showed you, that models all these axioms. It has infinite set. For every set there's a power set, but these in general, these are the ZFC axioms. And if you have something that models all of this, it's a model of mathematics or a model of set theory. And so we're interested in what are the axioms and what kind of things model them. And so there's just axiom of choice, axiom of regularity. And then I just mentioned that after Cantor started this like exploration into the higher infinities, it really made mathematicians look at like their theorems and say, what are the axioms we're actually using in math? So it made mathematicians look at themselves, or look at mathematics. I think that's one of the important things that Cantor did, was and eventually Gödel, like, and Zermelo, and writing down what are the axioms and then what can we say about them. Okay. Okay, so I guess this is about visualizing set theory. I guess it's like a lifelong project, or maybe not my whole life, but just a project that's happening slowly. But I'd like to be able to visualize each of the axioms. This is the axiom of extensionality, and so it says that two sets are the same if they have the same elements. So these two sets actually have just the two elements. I should even maybe put an equal sign right here. I did another one that's like axiom of pairing, that's kind of like this one, but I don't know if anyone out there is interested in trying to visualize the axioms. I think they get pretty hard. I think for me, it's like I can't really imagine how to do some of them. But if anyone is interested in that as like a project, I'm really interested in just having one painting or one image, maybe digital, for each axiom that somehow visualizes it. Just would be cool to try and have something like that. Okay, so large cardinals. So, and I didn't mention Gödel's incompleteness theorem, but Gödel showed that we can't prove, with these axioms, we can't prove the consistency of mathematics. Okay, and so large cardinals are connected to that because large cardinals are so big that they are models of these axioms. And so a cardinal capital is worldly if kappa is a model of ZFC, if it's a model of those axioms, if it's like its own universe, or if it satisfies all those axioms that I just stated. So because of Gödel's incompleteness theorem, we can't prove that these large cardinals exist, because if we prove they exist, then we can prove that the consistency of the axioms, which we can't prove. And I just want to mention a cardinal kappa is inaccessible. So the worldly, it's like the first, like the smallest large cardinal maybe. A cardinal kappa is inaccessible if kappa is greater than alpha naught, so it's uncountable, it's regular, and it's a strong limit. We saw regular, meaning like your cofinality is as long as you are. There's no backdoor, I think like a secret passageway or like a secret ladder. None of that. So it's kappa's regular, not like alpha sub omega, and it's a strong limit. So a strong limit, kappa is a strong limit if kappa is a limit cardinal and 2 to the alpha is less than kappa for all alpha less than kappa. So this is like omega, like 2 to the n is always less than omega. So omega is a strong limit. I think strong limits are actually pretty interesting because like we don't know that much about power sets, and like, I didn't mention this either, but like, are the alepphs that line up with the power sets? We don't really know, but these strong limits, they somehow know about power sets. They know at least about the power sets of things below them. But so an inaccessible cardinal is a large cardinal. It's also a model of ZFC. But why we might think that they exist, we can't prove they exist, but why we might think they exist, or why we have good reason to study them, is because they're like an uncountable version of omega. So omega is a strong limit, omega is regular, it's just countable. So an inaccessible is like it's like very nice. It's like I almost like the self-similarity property, or like this fractal nature, that like we have this thing that looks like omega, and it's up here, and there's like things to study about it. Okay, and my PhD thesis, I was studying inaccessible cardinals. I still like to study inaccessible cardinals and their degrees because they're very interesting. Okay, so that's it. And the last thing is some more visualizing. This is from The Higher Infinite by Kanamori. And these are just some more large cardinals in case that anyone hasn't seen some of these names before. And here's inaccessible and worldly's below them. Wooden and super huge. This is the Ramsey cardinal. It's inconsistent, but okay, well, thank you for listening either online or maybe people are here. So I'll just see if there's any questions, if anyone from the people that are here. Okay, and make sure if anyone has any questions, you can let me know or just maybe type a comment or something. But otherwise, thanks for listening, and yeah, I hope to talk more about ordinal art or axiom art with anyone if anyone's interested. Okay, so thank you so much for stopping by, and I'll see you later. Okay, so I'm going to stop the share.